Mount Etna unleashes an eruption unlike anything ever recorded. Scientists are shocked. This new eruption isn't just powerful, it's changing everything we thought we knew about how volcanoes work. Seismic alarms blared across eastern Sicily just seconds before the blast. A violent plume tore into the atmosphere, rising more than 10 kilometers high and glowing with an eerie metallic hue. Ash rained down like burning snow as molten material burst from the summit vents, moving faster and thicker than normal lava. Cameras captured the flow shimmering like liquid metal, increasingly getting brighter, denser, and pulsing with internal flashes of light. Nearby sensors failed as magnetic interference scrambled readings, leaving scientists briefly blind to what was happening. Within minutes, pressure gauges at the observatory spiked off the charts, then flatlined. Researchers realized Etna wasn't erupting in any pattern ever seen before. The composition, movement, and light signatures didn't match basaltic eruptions, which Etna is famous for. This was something entirely new, a geological event rewriting the rules in real time. Panic turned to awe as volcanologists watched the mountain's core unleash a force straight from Earth's mantle. But what's inside this eruption defies every geological rule known. When samples from the eruption reached labs in Catania and Rome, results defied every expectation. The crystalline structure was denser than any volcanic rock ever recorded, with traces of elements normally found only in meteorites and deep mantle formations. Under microscopes, it shimmered with a strange iridescence, a chemical fingerprint that didn't belong to Earth's surface geology. Geochemists identified isotopes of tungsten and nickel that formed under pressures impossible to replicate outside of the planet's interior. The conclusion was staggering. Mount Etna had somehow accessed a layer of Earth no volcano should ever reach. Some theorized that tectonic stress beneath Sicily had created a 1-in-a-million breach connecting the upper mantle to the crust. Others warned this could mark the start of a global shift in mantle convection, a deeper geological process forcing its way upward. Whatever the cause, the eruption wasn't just releasing magma, it was exhuming material from the planet's hidden core. The answer lies beneath Sicily, in a hidden fracture scientists just mapped. Using ground-penetrating radar and satellite tomography, researchers mapped a colossal fracture slicing beneath Etna's southern slope, which is a structure stretching more than 20 kilometers deep into the crust. The imagery showed branching tunnels connecting Etna's magma chambers to far older volcanic systems buried below the Mediterranean seabed. It's as if the mountain had tapped into a forgotten plumbing network of ancient eruptions. Data revealed molten material rising through this conduit at extreme pressure, moving faster than any magma ever recorded at Etna. These readings matched signatures found only in extinct supervolcano systems, suggesting Etna was now behaving like one on a smaller but rapidly evolving scale. Seismographs captured rhythmic pulses, tremors that repeated in near-perfect intervals, hinting at a continuous surge of material from deep inside the Earth. Geologists compared it to a magma elevator, hauling primitive rock straight from the mantle toward the surface. The deeper the source, the greater the instability. And with each pulse, the volcano's structure shifted a little more, widening the fracture beneath Sicily. And those deep tremors? They're starting to line up with something bigger. Within days of Etna's eruption, seismic stations across southern Europe had begun lighting up, and they were doing it in perfect sequence. All the while, tiny earthquakes rippled from eastern Sicily through the Ionian Sea, then curved along the Hellenic arc toward Greece. At first, experts dismissed them as coincidence, as if they were small tectonic slips caused by regional stress. But the timing was too precise. Every surge at Etna was followed by identical tremors hundreds of kilometers away, as if the Earth itself were pulsing in rhythm. Teams at the European Seismological Center traced the pattern and confirmed what few dared to suggest. Multiple magma systems beneath the Mediterranean were interacting. Pressure deep below the crust was migrating laterally now, and because of that, it was shifting faults that had been dormant for centuries. Some researchers compared it to a chain of loaded springs. When one releases, others begin to strain. They named it a magma pulse, a newly observed phenomenon that could link Etna to distant volcanic fields beneath the sea. If true, this meant Sicily wasn't facing an isolated eruption. It was part of a regional awakening, a geological domino effect capable of reshaping coastlines and rewriting tectonic history in real time. But the most alarming evidence isn't underground. It's what satellites see. High-resolution satellite images revealed something that sent shockwaves through the volcanology community. Mount Etna was physically shifting. The entire southeastern flank, a colossal slab of rock several kilometers wide, was sliding toward the Ionian Sea at an accelerating pace. And at first, the movement measured mere millimeters per month. But now it's advancing by centimeters each week. For now, that may sound small, but with billions of tons of rock in motion, even a few centimeters could mean absolute catastrophe. A sudden collapse would displace enough water to generate a tsunami that is capable of striking the coasts of Sicily, Greece, and North Africa within hours. Hence, scientists rushed to deploy GPS instruments, tiltmeters, and ocean floor sensors to track every tremor. The readings showed a disturbing trend. The sliding motion synchronized perfectly with Etna's deep magma surges. The volcano's internal pressure and its outer instability were acting as one system, each feeding the other. It wasn't just an eruption anymore. Etna itself was slowly tearing apart. Yet Etna's strange new chemistry suggests this story goes far deeper still. When geochemists compared Etna's latest magma samples with global databases, they found isotopic ratios that didn't match any modern volcanic system. But the trace elements, particularly helium-3 and neodymium, pointed more towards primordial mantle material preserved since Earth's formation 4.5 billion years ago. Such elements usually remain trapped deep below the crust, sealed off from surface processes. Their sudden appearance meant something unprecedented. Forces from the planet's interior were breaching boundaries that had been stable for eons. Etna had become a conduit between Earth's ancient core and its living surface. Researchers from Italy, Japan, and the US jointly concluded that this could indicate a shift in global mantle dynamics, like drastically increased pressure building deep within, that might alter volcanic activity across continents. In other words, Etna wasn't an isolated anomaly. It might be the first signal in a wider awakening beneath our planet's crust. For scientists, the implications were staggering. The deeper they looked, the more it seemed Earth itself was beginning to move in ways humanity had never witnessed. And just when scientists think they understand, Etna shocks them again. New thermal imagery shows lava fountains erupting from multiple new fissures that have formed along Etna's southeastern flank. The molten streams seem to pulse in rhythm with deep seismic activity, each surge more intense than the last. Tremor sensors inland are picking up vibrations that were previously going undetected, and although subtle at first, they are now climbing in both frequency and amplitude. Volcanologists realize that Etna's system is no longer isolated. The magma pulses are interacting with adjacent faults, amplifying stress across the region. The volcano's glow, visible from space, has intensified, and the chemical signature of the lava continues to defy classification, confirming the upward movement of mantle material. Emergency monitoring teams scramble to keep pace with the data, updating hazard maps hourly as models fail to predict what's coming next. Cities along the eastern Sicilian coast remain on alert, though officials admit the challenge. Etna's behavior is rewriting the rules of volcanology in real time. Every new observation raises more questions than it answers. Scientists now face the unsettling truth. This isn't just an eruption, but a pulse. A living geological event whose next moves could ripple far beyond Sicily, reshaping both landscapes and scientific understanding of volcanoes worldwide. Because whatever's happening beneath Etna may already be spreading beyond Sicily's shores.